Hello and good day. This video created by instructor Tom Kennedy of Milwaukee Area Technical College and member of IBEW Local 494. The information presented in this video is aligned with the Electrical Training Alliance Blended Learning System. Specific information included is to accompany the AC Theory Level 1, Lesson 2 of the curriculum. Something to note, there is some information stated in this video that is presented in the AC Theory Level 1 Lesson 3 video. Please feel free to watch the Lesson 3 video before this one to help better understand some topic items discussed in this video. The learning objectives covered in this video are: solve for total inductance in a series or parallel circuit containing more than one inductor. Find total inductive reactance in a series or parallel circuit containing more than one inductor. Solve for unknowns in circuits containing more than one inductor in a series or parallel when the values of other variables are specified. To review some previously learned information that will apply to this lesson, an inductor is a passive electrical component consisting of a coil of wire, which is designed to take advantage of the relationship between magnetism and electricity. The changing magnetic field in the vicinity of other conductors will cause CEMF to be induced into adjacent conductors. CEMF is the opposition to current in a circuit when there is a change in voltage. Inductance of a coil is related to four physical factors: the number of turns, the cross-sectional area of the core permeability, and the turn spacing or length of the coil. Faraday's law states, the EMF induced in a circuit is proportional to the time rate of change of the magnetic flux linking that circuit. In the figure of this inductive circuit shown here, there are two inductors connected in series. One item of information to note is that the magnetic fields of the inductors are not interacting with each other in any way. These are two inductors that are placed at a distance apart, to which the magnetic fields will have no effect on one another. Each of these coils of wire will produce inductance and oppose current flow in the AC circuit. Think about the factors that affect inductance. The addition of another inductor in series with inductor L1 essentially adds turns of wire to the first inductor, and the same applies for inductor L2 back to inductor L1. So in the end, the two inductors connected in series will have a combined effect and reduce the overall circuit current. By evaluating the opposition to current in this circuit, each inductor will have an inductive reactance. This inductive reactance can be calculated using the 2πfL inductive reactance formula, which is covered more in detail in Lesson 3 of AC Theory Level 1. Therefore, the 106 mH inductor L1 will have an inductive reactance of 40 ohms, and the 318 mH inductor L2 will have an inductive reactance of 120 ohms. These two quantities of opposition to current are connected in series. Therefore, the 40 ohms and 120 ohms will act to slow the current in an additive way. This can be stated using the same formula as the series resistance formula and replacing resistance with reactance. This works only because the circuit contains only inductive reactive components and the phase shifts of the components are equal. If these components were a mix of inductive, capacitive and resistive elements, this would not be the case and a different method of calculating opposition is required. The opposition to the current in this circuit will therefore be the 40 ohms plus the 120 ohms for a total value of 160 ohms of opposition. What if the frequency is not known in this circuit and only the inductance was known? That's okay, because if you replace the reactance X values in the formula with the 2πfL values, you can see that the 2π and frequency will become common factors. These common factors can be eliminated from the formula by dividing each side by the common factors. Thus, it can be stated that the sum of the inductance in henries is the total inductance of coils connected in series. This can be proven by adding the values of the henries of the inductors to get the total sum of inductance. The 106 mH and the 318 mH will total 424 mH. The 424 mH can be used in the inductive reactance formula, and the net result is the same 160 ohms of inductive reactance for the total circuit. Therefore, the two important formulas to remember are the inductive reactance total is the sum of the series connected reactance, or the total inductance in henries is the sum of the inductance connected in series. The value of 160 ohms determined in either method can be used to calculate total current for the circuit. In this example, the 240 volts divided by the 160 ohms of inductive reactance will result in 1.5 amperes of current. For this next example, the inductors shown connected in series in the schematic are placed so that 100% of the magnetic fields are inductively coupled with each other. The coils are placed so the magnetic field produced by each coil is in the same direction. The lines of flux interacting between the two coils will cause additional counter-EMF to be created. Therefore, additional factors of magnetic coupling are required for this type of circuit. When the coils are placed near other coils in which the magnetic fields are in the same direction. The term cumulatively coupled is used when the magnetic fields become additive or they accumulate. To calculate the total inductance in this circuit, an additional factor that includes the coefficient of coupling of the two coils is included and multiplied by the number of coils connected. The total inductance in the previous example was the sum total of the inductance connected in series. This is the foundation of calculating the total inductance, but the factor of 2m is now added to account for the coupling of the two additive magnetic fields. Without going into detail, calculating magnetic field strengths in the interaction take a bit of calculus, but an approximation formula for m can be used. Where k is a constant for the percent of the magnetic field that interacts between the two coils. When two inductors are placed on the same core with the same number of turns. The coefficient of coupling in this example is 100%, therefore the value of k will equal 1. Inserting it into the formula shown, the value of m will equal 106 millihenries. Using this value of m in the total inductance formula, the total series inductance is twice the value of henries than if the coil's magnetic fields did not interact. This is because the magnetic fields from each conductor will cut all the conductors of both coils. This results a total inductance of two series connected 106 millihenry coils that are cumulatively coupled at 100% will result in a total circuit inductance of 424 millihenries. This final value of inductance in henries can be used in the inductive reactance formula to find the total circuit inductance. Putting the 424 millihenries into the inductive reactance 2πfL formula, the total inductive reactance is 160 ohms. This inductive reactance can then be used to determine the total circuit current. If two of the same inductor coils were connected so that the magnetic fields overlap 100% and opposed each other, the opposing magnetic fields will not develop counter-electromotive force. The applied voltage polarity connected to the inductors are in opposite directions, the coefficient of coupling of the magnetic fields becomes subtractive. When magnetic fields of inductors are placed so the direction of the field flux is opposing, the inductors are considered differentially coupled, or the magnetic fields are subtractive, and the difference is all that remains to provide CEMF to oppose current. In this example, the coils are of equal value and the magnetic fields are 100% coupled. Calculating the multiplier m results in a value of 106 millihenries. This becomes subtractive from the series inductance, resulting in a net inductance of 0 henries. These inductors would have all the magnetic field's effects cancelled when connected with fields opposing, therefore resulting in what would be considered a short circuit. This is an important situation to remember, since there are many electrical motors, transformers, and lighting ballasts that have multiple inductors connected on the same core. If incorrectly connected, these inductors would act like a short circuit with a net 0 ohms. If two of the same inductor coils were connected so that the magnetic fields interact with an 85% coefficient of coupling and are cumulatively coupled, the magnetic fields develop counter-electromotive force acting to limit current in one another. An example of a 106 millihenry and a 212 millihenry coil connected in series with voltage polarity in the same direction will result in a net coefficient of coupling multiplier of 0.127. Placing this coefficient of coupling into the total inductance formula to calculate a total inductance of 572 millihenries. This now can be used to calculate the total inductive reactance in the 2πfL formula, resulting in a total opposition to current flow in this circuit of 216 ohms. These coils connected to a 277 volt source in this manner would allow 1.28 amperes to flow. If the two inductor coils from the previous example were connected so that the magnetic fields interact with an 85% coefficient of coupling and are differentially coupled, the magnetic fields would not develop counter-electromotive force to limit current in one another but would cancel the counter-electromotive force created. An example of a 106 millihenry and a 212 millihenry coil connected in series with voltage polarity in the opposite direction will result in a net coefficient of coupling multiplier of 0.127. Placing this coefficient of coupling into the total inductance differential formula to calculate a total inductance of 64 millihenries. This now can be used to calculate the total inductive reactance in the 2πfL formula, resulting in a total opposition to current flow in this circuit of 24 ohms. These coils connected to a 277-volt source in this manner would allow 11.5 amperes to flow. This can express the importance of connecting inductors so that the polarity of the connections are correct. A small error in wiring could result in a large current that can damage electrical equipment and create a hazard. To review series connected inductors. When the magnetic fields of the coils do not interact, the total inductance will be the sum of the inductors connected in series. When the magnetic fields have some type of mutual interaction, a coefficient of coupling needs to be determined and a multiplier used to calculate the net combined inductance of the series connected inductors. If the inductor's magnetic fields are cumulatively coupled in which the polarity is additive, the coefficient of coupling multiplier is multiplied by 2 and added to the total series inductance. If the inductor's magnetic fields are differentially coupled in which the polarity is opposite, the coefficient of coupling multiplier is multiplied by 2 and subtracted from the total series inductance. If more than 2 coils are interacting, additional calculations may be required. These examples were to provide a small understanding of what happens when inductive fields interact with coils connected in series. In the figure of this inductive circuit shown here, there are 2 inductors connected in parallel. One item of information to note is that the magnetic fields of the inductors are not interacting with each other in any way. These are 2 inductors that are placed at a distance apart, to which the magnetic fields will have no effect on one another. Each of these coils of wire will produce inductance and oppose current flow in the AC circuit, independently from the source for each branch of the parallel circuit. Therefore, the total current will be the sum of the current from each branch of the parallel circuit. A Kirchhoff's law equation can be written to express that the total current is the sum of the branches. Ohm's law equations for current can be substituted into the Kirchhoff's law equation. Since the voltage is the same for all branches in a parallel circuit, the voltage can be eliminated as a common factor on both sides of the equation. This gives us the reciprocal formula for inductive reactance, like the parallel resistance formula. The 2πfL inductive reactance formula can be substituted into the reciprocal formula, and the 2π and frequency can be eliminated as a common factor to both sides of the equation. This provides a parallel inductor formula using the inductance Henry values to determine total parallel inductance. This reciprocal formula can be used for many inductors connected in parallel, provided their magnetic fields do not have any interaction with one another. The product over sum formula that can be derived from the reciprocal formula can also be used to determine the inductance of 2 parallel connected inductors. The two 212 mH coils connected in parallel will have a total inductance of 106 mH. Using this in the inductive reactance 2πfL formula, we have a total opposition to current of 40 ohms. This will result in a total current of 3 amperes. The important formulas to remember for parallel inductors is the reciprocal of the total inductive reactance is the sum of the reciprocals of all inductors in parallel. The reciprocal of the total inductance in henries is the sum of the reciprocals of the inductance in parallel. The product over sum formula can be used to quickly calculate 2 values in parallel. Another way of evaluating the total inductance of 2 parallel inductors that have no magnetic fields interacting with one another would be to determine the inductive reactance of each branch of the parallel circuit. Using the 2πfL formula, each inductor would have an inductive reactance of 80 ohms. Use the inductive reactance of each branch to find the current in each branch of the circuit. Connected to a 120-volt source, each branch would draw a current of 1.5 amperes. The total circuit current would be the sum of the individual branches. Therefore, the total current in this circuit is 3 amperes. This total current can be used to determine the total circuit inductive reactance using Ohm's law formulas. 120 volts divided by 3 amperes provides a resulting total inductive reactance of 40 ohms. This can be put back into the inductive reactance formula to solve for inductance. The total inductance of this parallel circuit is 106 mH. This next example is to determine the inductance of 2 identical inductors connected in parallel with a coefficient of coupling that is at 100%. The product over sum formula will need to take into consideration the magnetic field interaction. When the magnetic fields are cumulative, the formula has m squared subtracted from the product and 2m subtracted from the sum. If two 212 microhenry inductors are placed in parallel on the same core to which all of the magnetic fields interact, the mutual inductance M factor is the same as the original coil, and the total inductance calculated with the revised product over sum formula ends up as 0/0 or undefined. This is not a short circuit, nor is it infinite reactance. The approximation used for the mutual induction formula does not take into consideration that if two identical coils are wrapped around the same core, the CEMF and resulting current will be shared between them identically. This acts as if a single larger conductor was used to make the two smaller parallel inductors. The inductance of two identical parallel inductors will result in a total inductance that is the same as one inductor. Therefore, in this example, the total inductance is 212 millihenries. Putting the total inductance into the inductive reactance 2πfL formula, the total opposition to current will be 80 ohms. Calculating for total current will result in a total current of 1.5 amperes in this circuit, each inductor having half of the current passing through it. Determining the total inductance of two coils connected in parallel, where the magnetic fields are differentially coupled at a factor of 100%. These coils are connected to the voltage supply in a manner that the direction of current is opposite one another, and the lines of flux are essentially cancelling one another out. The coefficient of mutual induction M factor calculates to a value of 212 millihenries. The product over sum formula is amended so that the 2M is added instead of subtracted from the sum portion on the bottom. The calculation of total inductance for this circuit comes out to 0 henries. The resulting inductive reactance for 0 henries would be 0 ohms of opposition caused by the inductance of this circuit. The resulting current in this circuit would only be limited by the resistance of the wire that is used to construct the coils, and the inductance would have no effect on the circuit. Depending on the conductor resistance, these parallel inductors could act like a short circuit and cause large currents to flow, damaging electrical equipment and causing hazards. One should take great care to make sure to pay attention to polarities when making connections of inductors to avoid such issues. Where parallel coils are connected and are cumulative with a coefficient of coupling at 85%, the 106 millihenry and 318 millihenry inductors will have a mutual inductance factor of 156 millihenries. The parallel inductance will be 84 millihenries. This will result in an inductive reactance of 32 ohms and a total circuit current of 3 3/4 amperes. If the individual current for each coil is found and added, the 106 millihenry coil L1 will have an inductive reactance of 40 ohms and the L2 318 millihenry coil will have an inductive reactance of 120 ohms. The current expected in L1 would be 4 amperes, expected current in L2 would be 1 ampere respectively. The total current would be expected to be 4 amperes. This would be an incorrect answer. Since the CEMF of one coil will create an opposition to the source for the other coil, in the shared magnetic field, the net current will be lower than two individual coils acting independently. Where parallel coils are connected and are differential with a coefficient of coupling at 85%, the 106 millihenry and 318 millihenry inductors will have a mutual inductance factor of 156 millihenries. The parallel inductance will be 12.7 millihenries. This will result in an inductive reactance of 4.8 ohms and a total circuit current of 25 amperes. These last two examples are connections of different inductors in parallel with interacting magnetic fields. The use of parallel connections of differing inductance are present in single-phase motors for the control of motor speed. The proper connection with the polarity of the magnetic fields becomes important considering the last two examples. Parallel inductors that have no magnetic coefficient of coupling can use the regular parallel formulas to find the total inductance. When parallel inductors have magnetic fields that interact, the coefficient of coupling will create additional CEMF or reduce the CEMF present in the inductors. These need to be included when calculating total inductance of parallel coils. Thank you for watching this video. You should be prepared to complete AC Theory Level 1, Lesson 2, but feel free to consult the textbook and LMS resource to aid you in completion of the online quiz.